3D printing makes it possible for anyone to fabricate complex 3D shapes, but the resulting objects lack interactivity. Electric circuits can be used to create interactions with light, sound, and motion. However, combining 3D prints and electric circuits is a challenge. The user has to modify the 3D design to include hollows large enough for the circuit, fixtures to hold it in place, and wire routing channels to connect components. In this paper, we present SurfCuit, a system that supports the design and fabrication of circuits on the surface of 3D prints. Here is our fabrication workflow. First, we show our SurfCuit design system. The user begins with a 2D schematic diagram, placing symbols that represent electric components and drawing traces that connect the components together. Then, the user switches to our 3D interface to lay out the circuit components and traces on the surface of the object. Smooth 3D traces on the surface are generated in real time in response to user input. If the trace generation fails, the system annotates the failure and prompts the user to add or move points. The user can create an organized schematic by adding points or changing connectivity. In the 3D layout, the main challenge is to position the components and traces such that there are no intersections between the traces. This is an iterative process. The user interactively edits the traces to resolve intersections. The system shows the corresponding 2D schematic component during 3D layout editing to facilitate the user's understanding of the circuit. Finally, when the user presses the print button, the system generates a surface mesh with holes and channels corresponding to the component and trace locations. These surface features will assist in the fabrication process. After 3D printing, the user manually places strips of copper tape in the channels. Then, the user inserts small copper tube segments in the holes. Finally, the user solders the traces, tubes, and components together to make a robust 3D circuit. Here is an example: a police car with blinking lights and a siren sound generated by a speaker. 3D printing plastics melt into viscous fluids at roughly the same temperature as the solder melts. After the plastic cools, it has bonded to the circuitry. We perform destructive testing to compare the robustness of our fabrication process against a more basic strategy where copper tape is simply affixed to the object using its adhesive backing. After brushing these test samples for 1 minute, the basic circuit was damaged severely and stopped functioning. On the other hand, our circuit is very reliable and continues to function. Here are more examples of SurfCuit objects. This bird incorporates a light theremin circuit that generates chirping sounds responding to the motion of the user's hand. Because we can use the whole surface, it is possible to fit a circuit even on this very small object. This smartphone stand amplifies the audio output of a phone. This Christmas tree contains a large number of traces in quite a complex pattern. The circuit illuminates 13 LEDs with a synchronous timing. Our fabrication strategy produces traces that are highly conductive, allowing us to drive servo motors, which in turn make it easy to add some dynamic motion to a 3D print. This cat model waves its hand and shakes its head while blinking its eye. Here is another example, an octopus tentacle that contains a touch-activated USB fan and can be mounted on a computer monitor. Our solid copper traces support enough current to drive a DC motor. Our spy squirrel contains a concealed microphone and FM transmitter. The circuit is fully enclosed inside the body.
Can you hear my voice? Can you hear my voice? Hello, hello. Can you hear my voice? Can you hear my voice? Hello, hello. Can you hear my voice? Can you hear my voice? Hello, hello. Can you hear my voice?
Finally, this ornamental face design contains a high voltage circuit that drives an embedded EL wire. In this example, we used parts of the circuit as aesthetic design elements. Thanks for watching.